Okay, so this question is on single slit diffraction and Rayleigh's criterion. So you are given wavelength 590 nano. Okay, so you see the B. Okay, this is a single slit diffraction. So immediately we need to know that we need this formula. Okay, for the first order minima, lambda over B. Okay, sin theta equals lambda over B. So we'll be using this. Okay, so the light that is passing through and the variation of the angle is shown in figure 4.2. Okay, so it's given to you the single slit diffraction pattern. Determine the magnitude of theta 1. So you can see that theta 1 is actually the first order minimum. So it's pretty straightforward. I will just write at the bottom. So for A part 1, sine theta 1 equals to lambda over B. Okay, first order. So nothing very special. Okay, and lambda is given to you as 590 nano. Okay, B is given to you here, 0.2 mm. Okay, here. So it will be 0.20 times 10 to the power of minus 3. Then after that, just need to use your calculator. Okay, so let me just type in the calculator. 590 times 10 power minus 9 divided by 0.2. Okay, divided by 10 power minus 3. Then you'll get around 0.00295. It's pretty small. So theta 1, in terms of, they did not ask for uh radians or degrees. Okay, so I will just use radians. Let me just change the calculator to radians. Because it's a small angle, so by right, what happens is that it should be almost the same. So if you use theta 1, should be approximately 0.00295 radians. Okay, so that should be the magnitude of theta 1. Okay, why I use the radians? Because radian is more like the SI unit of angles. Okay, so next one, theta 2. You'll see that from this diagram, theta 1 is first order, theta 2 is by the time theta 2 is a third order. Now, this formula now is not in A-level syllabus already, which is generally sine theta equals to m lambda over b. Okay, not in the Singapore syllabus at least. Overseas, yes, but not in the Singapore one for now. So m is the mth order minima. Okay, just that for our case, usually we use m equals to 1. But for this question, probably they will need you to use this, okay? Most likely does not come from any, I'm not so sure, not from any prelim papers, maybe an overseas paper. Okay, so for theta 2, what happens is that you'll need sine theta 2 equals to 3 lambda over b now, because it's a third order minima. Okay, so based on this, because this is lambda over b, we know that it's going to be 3 times 0.00295. It's still pretty small. Okay, so if you calculate, you should get theta 2 as, theta 2 as 0.00885 radians. Okay, and then calculate the width in mm of the central maximum of the diffraction pattern. So here, what happens is that it is 0.75 meters. There are two ways to do this. Okay, let me show you the standard way. The standard way is to use, let me see. Okay, this one not possible. The standard way is to use a right angle triangle. Okay, so you probably have something like that. Then after that, up, and then the last one, let's put it here. So you probably have here as the theta 1. This is your 0.75 meters. Okay, let's try again. So this angle here, theta 1, this is 0.75 meters. And this is half of the central maximum. Okay, the central maximum is actually this line here. Or if we were to do it on here, it will be, imagine another theta here. Okay, for theta 1, it will be this line here. That's the central maximum. But I'm taking the first triangle, this part. Okay, I'm taking this part. So that is where this is here. So let's say we let this be y, and we know that y divided by 0.75 equals to tangent of theta 1. So tangent of theta 1, okay, is still, because of small angles, it's still about the same. So you multiply by 0.75, you get around 0.0022125 meters. And the width, which should be twice of it, times 2, you will get 0.00443 meters for 3SF. Okay, so that is the, oh, they wanted in mm. Okay, so let me just change it to mm. So we have 1 2 3, which is approximately, okay, so approximately is the previous part, so we should have the approximately here. Okay, because it's rounded off, so it's equals to 4.43 mm. Okay, alternatively, now this one is only possible when the angle is small, which it is. Okay, we can use S equals to R theta. Okay, although this is the arc length, S is the arc length if you recall. This is S, this is R, this is theta. Now, this thing here, this S here, is approximately straight if theta is very small. Okay, very close. And theta is indeed small here. And because we have theta 1 on top and theta 1 below, so what happens is that the total angle here is actually 2 theta 1. Okay? So we can say that the central maximum, the width of the central maximum is actually S equals to R. R in this case is 0.75 meters times 2 theta 1. You'll get the same answer. You'll realize that it's actually the same values here, which is 0.00443 meters, okay, or 4.43 mm. Same. Okay. Last part. Determine the angle between the two beams of light such that their diffraction patterns are just resolved. Explain your working. So this, when you see the word just resolve, immediately it's going to be Rayleigh's criterion. Okay, so basically you have two beams of light. You have just a single slit here. Your beams of light are somewhere here, and they will form a pattern on the screen. So this is the screen. Okay, this is just a rough sketch that is not to scale. So you wanted the angle here. Okay, this is a standard Rayleigh's criterion setup. Okay, so for just resolved, because you need to explain the working, you need to write a little bit. For being just resolved, what happens? For just resolved, okay, the angle is approximately lambda over b by Rayleigh's criterion. Okay, Rayleigh's criteria. So the theta is equals to lambda, which 590 times 10 power minus 9, divide by b, which is 0.20 mm. This is the same value as theta 1 earlier. They repeat the same thing. So again, this will be 0.00295 radians. Okay.